In the last presentation, we identified the need to treat wastewater for its safe, reliable, and unlimited reuse. But what are the requirements for an on-site treatment system? And why may they be different from centralized treatment systems? To answer this, we should briefly revisit the unique conditions that on-site systems must cope with. Changing wastewater quality and quantity. The system may be used by non-professionals and in close proximity to public and children. Thus, it must be durable and reliable. It should be inexpensive and low maintenance, as it must be paid for and operated by the homeowner. Overall, any on-site treatment unit should be feasible for small owners or operators and should not require complicated or frequent professional maintenance. Since these systems are installed in close proximity to people, they should be aesthetically pleasing with no strong smells or mosquitoes. For most part, all of these systems should mainly treat three components: suspended material, or TSS, organic matter, and pathogens as indicated by the total suspended solids, BOD, and fecal coliform. A range of physical, chemical, and biological solutions are available in order to address the previously mentioned unique conditions. In the next slides, we will discuss each of these solutions, starting with solid removal. There are several methods to remove coarse and suspended material based on its properties. As one can see, the methods depend on the solid particle size, ranging from large solids to fine ones. Mostly these methods include screening and sedimentation and finer filtration units, such as drum and sand filters, and for the very fine dissolved particles, all sorts of membrane technologies, which will be discussed in other section. Larger solids are typically trapped by screens such as this to remove waste like wipes, sanitary products, and larger debris. Removal of suspended solids with an average diameter greater than 75 microns can be efficiently and economically performed using a sedimentation basin. In principle, a particle will settle and accumulate as sludge at the bottom of the tank if the gravity force pushing it down is greater than the drag and buoyancy forces that push it upwards. Other than particle size and properties, the liquid properties, flow pattern, basin dimensions, and several other factors affect sedimentation. But sedimentation tank design is beyond the scope of this course. The supernatant, the water from which the particles have been removed, flows out from the upper part of the basin, but not from the basin surface where fats, oil, and grease may accumulate. The sludge at the bottom must be drained from time to time, as well as the floating scum. Sedimentation basins can have several designs and shapes, as can be seen in the following slides. Smaller particles can be removed or filtered out by devices such as drum and sand filters. In the drum filter, water passes through a screen with a known pore diameter. The trapped solids are being backwashed and removed from the system with clean water that is emitted via spray nozzles whenever the screen clogs and removed from the system. As can be seen, in the sand filter, water flows via sand layer. The clean water is flowing through and the solids are trapped between the sand grains. Once the sand is clogged with particles, the pressure increases and the sand is backwashed with clean water and the solids are removed from the system. Let's move on and discuss the basic biological treatment principles. The supernatant that now contains the smaller suspended and dissolved organic matter is mineralized or decomposes biologically by microorganisms, aerobically, meaning in the presence of oxygen, and or anaerobically, in the absence of oxygen. In this process, the volume of solids is reduced and the water quality is improved. The degrading microorganisms can be either suspended in the water or more typically in on-site units attached to high surface area filter media, such as plastic beads or tuff, as can be seen in the following slides. Under aerobic conditions, the organic compounds are mineralized into carbon dioxide, water, energy, and dissolved minerals such as bicarbonates and ammonia in a process called catabolism. Part of the energy and the nutrients are used by the microorganism for the synthesis of new compounds and reproduction in a process called anabolism, and part of the energy is used to sustain cellular processes. Once food is depleted, microorganisms start to feed on their own protoplasm for cell metabolisms in the presence of oxygen, and more carbon dioxide, minerals, and water are produced. Schematically, this biological mineralization can be described as follows. Under aerobic conditions, organic matter or biomass plus oxygen is converted to carbon dioxide plus water plus energy, ammonia, and minerals. In the anaerobic process, organic matter or biomass is converted to carbon dioxide, methane, water, ammonia, and minerals. Disinfection is used to remove pathogens. Most commonly, chlorination is used, and more recently, also low-pressure UV. Chlorine is an oxidizing agent which damages the microbial cell membrane and prevents it from multiplying. There are numerous ways to supply chlorine, but one of the simpler methods is to flow the treated water via slow-release chlorine tablets. The flow rate should allow enough contact time between the tablets and the water to achieve a free chlorine dose of 0.5 to several milligrams per liter chlorine for at least 30 minutes. This ensures efficient pathogen disinfection. When using UV disinfection, the water must be exposed to the UV light long enough so the UV dose that corresponds to the lamp's energy and the contact time are great enough to disinfect the water. Typically, flow-through UV lamps such as in the picture are used on-site. It should be noted that the membrane technology for wastewater treatment that is discussed in the course is becoming more commonly used, but it's still too expensive and sophisticated for widespread on-site use. You may have noticed that I ignored the fate of nutrients, particularly nitrogen, during the treatment. While nutrients may be considered as pollutants if they are released into the environment, they may also be a resource if the treated wastewater is used for irrigation. Thus, the biological treatment may vary for different scenarios. Briefly, as outlined in the slide, much of the ammonia is biologically transformed into nitrate under aerobic conditions in a process called nitrification. Under anaerobic, or more accurately, anoxic conditions, which means without oxygen but in the presence of nitrate, the nitrate can be biologically reduced to nitrogen gas through a process called denitrification. It is clear that if we want to save the nitrogen in the water, we should try to avoid denitrification, whereas if we want to remove the nitrogen from the water, we should pursue it. There are several other reactions that are related to the nitrogen cycle, which are quite complex, but they are beyond the scope of this presentation. The fate of nutrients and their recovery was further discussed by Dr. Oded Nir. Next, we will exercise some of the concepts we learned and will dig deeper into the biological treatment principles.